Dear Makkals, Kulandeigals, Bechoms, how are you? Hope you are fine and safe. This is Riju and PSK classes, laws of motion. In the last class, I left you with the homework. Hope you have done that one, and that was like finding the action and reaction pair in a given system. And okay, in that system, there was a ceiling given, and on the ceiling there was a string connected, and at the end of the string there was a block, and all below you have your Mother Earth. I asked all action reaction pairs. Okay, let us start from the ceiling. There is force on the ceiling by the string and force on the string by the ceiling. These are equal and opposite. There is force on the string by the block, and there is force on the block by the string, action reaction pair. Now go to block and earth. There is force on the block by earth, and there is force on the earth by the block. These are action reaction pairs. Then there is string and earth. So there is force on the string by earth and force on earth by the string, action reaction pair. Then take earth and the contact ceiling, force on the ceiling by earth. There is the pair for that one, force on earth by the ceiling. But is there a force on the ceiling by the block? Is there force on the ceiling by the block? There is no such force, because block cannot directly apply a force on the ceiling without a physical contact, but earth can do that one. But I am saying, I just forget one point that, like if you consider gravitational force, then the block also has got a force on the ceiling. But we are neglecting the gravitational force of all these things, but we will consider the gravitational force earth. Manasilayo. If you consider all gravitational force, then there is force between the ceiling and the string, force between the ceiling and the block, gravitational, but these are not gravitational forces. Okay, I will tell you which are the gravitational forces here. Okay, this one, the action reaction pair of earth and a body, and this one and this one. These are gravitational forces. Whatever these things, these are contact forces, these are electromagnetic force. Force between the contact and the string here is electromagnetic, this force is electromagnetic, all other forces are gravitational force. If you want to consider all gravitational forces, then there is force on the ceiling by string, gravitational, there is force on the block by the ceiling, gravitational, but these are negligible, so we will not consider them. Okay, so we normally consider only gravitational force between earth and objects, not a gravitational force between them, but we will consider the electromagnetic contact forces between all the objects, and there is no electromagnetic contact force between the earth and the block, because there is no contact. So these are the important action reaction pairs. Okay. Now we are coming to another important concept in physics. It is called equilibrium of a body. Equilibrium is the absence of net force. Equilibrium is the absence of acceleration. If there is no acceleration for a body, we will say it is equilibrium. There are different types of equilibrium, okay, which can be discussed in maybe in the next chapter. But I will say, like if a body is rolling or rotating, there is rotational equilibrium. If a body is moving in a straight line, it is called translational equilibrium. We are discussing about translational equilibrium. You can see that word here, translational equilibrium. Okay. First of all, what is the condition for translational equilibrium? That is very simple. If all forces working on a body balances each other, that is equilibrium. And such forces which act at the same point are called concurrent forces. Forces acting at a common point is called concurrent forces. A body under the action of concurrent forces is said to be in translational equilibrium if there is no change in the state of rest or the change of state of uniform motion along a straight line. That means it should be either at rest or in uniform motion. That means acceleration should not be present. If there is no acceleration, it is in equilibrium. The necessary condition for equilibrium is that the resultant force must be 0. The net force must be equal to 0. And for equilibrium, we will write the total force equal to 0 along x-axis, y-axis and z-axis. The components must be equal. I tell you this, if there is a body, this will be in equilibrium, okay. It is in equilibrium if all forces acting to this side balances all forces acting to that side. Leftward force equal to rightward force. So, I can say leftward force equal to rightward. Okay. Then upward should be equal to downward. Upward force should be equal to downward force. And this will not generally come frontward, and actually ahead of the body, frontward should be equal to backward. And this frontward is not a word that we generally use, frontward. Okay. This is how you understand. If there is a body to be in equilibrium, the force acting to the left and the force acting to the right should be balanced. Force acting upward, force acting right downward should be balanced. Force acting this side should be balanced to force acting to the other side. If I call this as x-axis, this is y-axis, then this is your z-axis. That's why it is say net force on x-axis should be 0. Sigma f x equal to 0 means left right should be equal, that is leftward equal to rightward. It means that sigma f in the x direction should be equal to 0. Upward downward equal means the total force acting in the y direction must be 0. Front back equal means the total force acting on the z direction must be 0, then the body is in equilibrium. Fine, this is the condition for equilibrium. And in equilibrium again there are two possibilities. One is called static equilibrium, where the body is at rest. Here a body, there is a ball hanging from a wall, it is at rest. The total force acting on the body must be 0. This is called static equilibrium. Net force is 0, body is at rest. And there is another equilibrium which is called dynamic equilibrium, where net force is 0, body is in uniform motion. There is a raindrop. On a raindrop, gravitational force will act downward. From air, there is a force acting in the upward direction. As a result, that will be in uniformly moving downward. Static equilibrium, dynamic equilibrium. In dynamic equilibrium, this is an example, raindrop, uniform velocity. Okay. So, static equilibrium and dynamic equilibrium. Now, for analyzing equilibrium of a body about concurrent forces, you can see there is a point and there are three forces acting on it. All forces are acting at a point, so it is called concurrent forces. Then we can use Lamy's theorem. You might have studied this in motion in a plane. In motion in a plane, you studied parallelogram law. It is also known as law of cosines. This is law of sines. In the same derivation, you had done this. It is also known as Lamy's theorem. It is very simple. You have three. This is applicable only for three vectors, three forces. There are three forces acting, and this is in equilibrium. That means they are balanced. If they are balanced means, what does that mean? You are familiar with the word resultant, right? So, this F1 and F2 will have a resultant in this direction, F3 will cancel it. Or F1 and F1 and F3 will have a resultant and F2 will cancel it. Or F3 and F2 will have a resultant and F1 will cancel it. That is how they cancel. In such cases, you can write this one. You take the magnitude of one force divided by angle between other forces. This angle is alpha. F1 by sine alpha. Take one force divided by sine of the angle between the other forces. Similarly, F2, and what is the other vector? F1 and F3. F2, F1 and F3. F2 should be divided by angle beta, okay, and F3 should be divided by angle sine gamma, if it is balanced. So, this is a very easy tool to solve questions in equilibrium. Let us work out one. This is from NCERT. Read it clearly, carefully. A mass of 6 kg is suspended by a rope of length 2 meter from ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope as shown. What is the angle the rope makes with the vertical in equilibrium? Take G equal to 10 meter per second square, neglect the mass of the rope. This is the question. Think, visualize. There is a diagram. Now I can just give a demo for this thing. Say this is provided by my cameraman Jittu, and this is his charger. Okay. Now if suppose I hold it somewhere here, this is not vertical because this is not that heavy. So assume that this is hanging like this, and if I take the midpoint and pull it to one side, you can see that it takes a shape like this. It takes a shape like this. So that means there is a force acting here in the horizontal direction like this. And this is taking, see the string becomes inclined to the vertical. And that definitely depends on the amount of force that I apply. Larger force means it can be almost horizontal. No force means it's vertical. That is given in this diagram. Okay. Now details are given. Okay. So I am redrawing that one. The mass of the body was given as 6 kilogram and G was equal to 10. So we can calculate weight of the block as mg. So weight is mg, which is 6 into 10, which is equal to 60 Newton. And 60 Newton will act downward. Okay. Now when you stretch a string like this, there is a force in that one. Okay. See, I am pulling one side of the string and that force is there on my other side because this will transmit that force, and that force is what we call as tension. And that tension is marked here, tension here and tension here. Okay. Now this is the point. This is the point. That is the 50 Newton force applied, this is 60 Newton, and the string is making, so the string will make an angle theta here which can be equal to this theta. So now look at the point, the center point. There is a force of 50 Newton to this side and there is a force of 60 Newton to this side, and there is a string force. Oh, I think I should be explaining one more point. See here, this point. This block is at rest. So if something is hanging and is at rest, its weight is supported by force in the string. So from the block diagram here, the block has got 60 Newton acting downward and there is a force acting in the upward direction, that is T1. So what should be the value of T1? T1 is equal to 60 Newton. Now take the central point. There is this 50 Newton acting to the right side, and there is this, no, this is T2, I am sorry, this is T2, this should be T2, and this T2 will be acting downward, it will be pulling the point downward, and that is equal to 60 Newton. And there is this force acting in this direction, it is called T1, and the angle is theta. Now you can use Lami's theorem, or you can use a resolution of vectors. Any one of these is okay. You want to find the angle theta. Okay. So let us use resolution of vectors first. We know this vector, if you imagine it is going like this, it is going from right side to left side and bottom side to top side. That means there is a component in the upward direction and another component in the leftward direction. This component is near, adjacent to the angle. So this is T1 cos theta and this is T2 cos theta. So after resolving, you can say you have resolved this vector. So that is not existing now, it is not there. Instead of that you have these two components. So this is not there. Now you can see there is a leftward force, there is a rightward force, upward force, downward force. So you can say if it is in equilibrium, we can say the leftward, I made a mistake, this must be sin theta, that must be sin theta, this must be T1 sin theta, that is T1 cos theta. Okay. So leftward T1 sin theta should be equal to rightward 50, and the upward T1 cos theta should be equal to 60. If you divide these two, T1 will cancel, sin theta by cos theta will give you tan theta, equal to 5 by 6. So, you can write your answer like theta equal to tan inverse of 5 by 6. That is the way you do the question using resolution of vectors. Now, let us do this using Lami's theorem. Let us apply Lami's theorem. Let us take the midpoint. Let us take the midpoint, and there is a force acting here which is 50 Newton. Okay. There is a force acting here which is 60 Newton, and there is a force acting here which is T1. And this angle is theta, and this angle is 90 degree. Okay. Now, this whole angle is 90 plus theta, and this angle is 180 minus theta, because here the straight line makes 180 minus theta. Now, apply Lami's theorem. Take T1, you divide it by, T1 should be divided by angle between the other two, which is sin 90, equal to not T2, T1 is divided. Now, 50 should be divided by sin of 180 minus theta, and that is also equal to 60 divided by sin of 90 plus theta. Okay. You want theta, you do not want tension. If you want tension, you can calculate from this one. If you want theta, you can take these two equations, and this is like 50 divided by sin 180 minus theta, that is equal to sin theta. This is 60 divided by sin 90 plus theta is cos theta. Okay. So, we can say this will give you sin theta by cos theta. Take sin theta to that side, sin theta by cos theta, take 60 to this side, will give you 5 by 6, which implies that which implies directly that theta is equal to tan inverse of 5 by 6. You get the same result. Okay. In certain situations, this method will be easy. In certain other situations, that method will be easy. It depends on you. Okay. Either method is equally good. Fine. But many times I find resolution is easy. Okay. Now, next question, a smooth sphere of radius r and weight w hangs by a light string of length r. That details are not given in the diagram, it is given in the question. Okay. The string has got a length r and the radius is also equal to r. One end of the string is fastened to a point on the surface of the sphere, while the other is fixed to a point on the smooth vertical wall. Determine the reaction of the wall and the tension in the string. Okay. So, now if you see the body is at a static equilibrium, and how many forces are acting at the center? At the center there is a weight acting. At the center the force from the wall will effectively act in this direction. So, there are 3 forces acting there. Okay. So, this is tension, this is the reaction from the wall, determine the reaction from the wall, and this is the weight of the body. Its weight is given as W. Okay. And this angle should have been given. Okay. Say this angle was missing, it was in the original diagram, okay, but it missed here. Okay. Now, how do we find out the reaction? Just like the previous case, this tension can be resolved into, you take this angle as theta, okay, this is T cos theta and this is T sin theta. So, we can say for equilibrium what is required, T sin theta should be equal to R and T cos theta should be equal to W, which gives you tan theta is equal to R by W. So, the reaction is nothing but W into tan theta. Reaction is W tan theta. See, reaction is also T sin theta into R, but you do not know tension, that is why I am writing that in terms of W, R equal to W tan theta. But what is tan theta here? What is tan theta here? If the sphere is in this position, this must be its radius. This is 2 times the radius. So you have a triangle here. You have a triangle where hypotenuse is 2r and this side is r. Okay. And this angle is theta. So you definitely can find out tan theta from this thing, or you can find out sin theta and cos theta. Okay. Sin theta is nothing but r by 2r and cos theta is, it's very easy actually. This is theta, right? So what do you define sin theta? What is sin theta? Opposite side by hypotenuse, that is r divided by 2r. So that is 1 by 2, which implies that theta is equal to 30 degree. Theta equal to 30 degree. So this will give you W into tan 30 degree. And tan 30 is 1 by root 3. So this will become W by root 3. So using the condition of equilibrium, you can easily solve and find out. If you want tension, you can substitute that here. Tension will be equal to, we can say tension equal to sin theta by r, that is equal to 2 times the reaction, 2W by root 3. Tension will be equal to 2W by root 3. So this is also possible. Okay. Let's do another question on equilibrium. The adjacent figure is a part of a horizontally stretched net. There is a wire net which is horizontally stretched. Okay, level. Section AB, this part is AB, is stretched with a force of 10 Newton. Here there is a force of 10 Newton. What is the tension in the section BC and BF? Okay, I think I will enlarge the diagram. Now this is easy. Okay, it is equilibrium. They are saying that this point, there is a force here. This is stretched by a force of 10 Newton. You want to find out the force here as well as the force here. Now take this point. Take this point here. That point is here. And there is a force acting in this direction. How much is that one? That is equal to 10 Newton. And you can see there is a force acting in this side and there is a force acting in this side. Due to symmetry, these two forces must be equal. And see, the angles are given, very friendly angle. This is 120 degree, this is 120 degree. Okay. So you need to find out the force in these two sections. Okay. Now do like this. This tension can be resolved into one component to this side. This is like if this is 120 degree, this must be equal to 30 degree. So this is T cos 30 degree to this side, and this will also have T cos 30, and they will cancel each other. That's why it's in equilibrium. Now the other component, this will have a component called T sin 30, and this will also have a component T sin 30. So for equilibrium of a point B here, equilibrium, leftward should be equal to rightward, that they are equal, and upward should be equal to downward. So how many forces are there in the upward direction? There are two tensions, 2 into T into sin 30 is 1 by 2. Two of them, sin 30 is 1 by 2. So 2T into 1 by 2 is equal to downward force of 10 Newton. That means T equal to 10 Newton. Okay, so this will have 10 Newton, this will have 10 Newton. But if you are very good in vectors, then you will understand that this was not required. This calculation was not required. A point where 3 equal magnitude forces are acting at 120 degree, then if this is 10, this should be 10, that should also be 10. That was the idea. Okay. Now, I think this you can do from the previous example. So I will not be doing this, I will not be discussing this in the next class. So this you just try. Body of weight is given 2 kg, tension T1 should be calculated, angle is given. In the previous case, the angle was not given, you are given 50 Newton force here. So I will say, I'm sorry. So from the same idea, you can find out the tension T1. Okay, you have that equation, remember tan theta equation, then you can apply that one here. So this will not be discussed in the next class. This one, 2 persons are holding a rope of negligible weight tightly at its end so that it is horizontal. So 2 persons are stretching a string horizontally. Okay. A 15 kg weight is attached to the rope at the midpoint, which now which no longer remains horizontal. So what will happen if you have a string stretched like this, and suddenly if you hang something at the middle here, then that will bend down. It won't be horizontal. Now by pulling it, you can make it horizontal. Or we may try to make it horizontal by pulling. Then what is the force required, minimum tension required to completely straighten the rope? That's what they have given, and the tension is given in terms of kilogram. Okay, they have given 15 kilogram, 7.5, infinitely large, not possible. Let us work out this using the concept of equilibrium that we have learned. So initially the string was horizontal, but after hanging the weight, the string will become like this, and this is where the 15 kilogram body is hanging. If you take a g, the value of g as 10 meter per second square, 15 kilogram will have a force of 150 Newton acting downward. So that 150 Newton will act here. Okay. Assuming that this point is in equilibrium, this block will be in equilibrium. If there is 150 Newton acting downward, then the string will also have 150 Newton. That's our experience from a previous problem. So that is it. Now look at this point. This is in equilibrium, and this is at the midpoint, right? So the force on the two sides must be same because it is symmetrical. It is symmetrical. This is exactly now like the previous question. So let me do that here. Okay. So there is a point, there is a force of 150 Newton acting downward. Okay. And say there is a tension acting in this direction, there is a tension acting in this direction. Let us say this, like say this is x axis, this is y axis. Naturally, you can resolve the tension by assuming certain angle. Assume that this angle is theta. So by symmetry, this angle will also be equal to theta. So the tension will have a component in this direction which is called t cos theta, and this tension will have a component which is also equal to t cos theta, and this tension will have an upward component which is equal to t sin theta. This will have another component which is called t sin theta. Exactly like the previous question. For equilibrium, what is required? Left and right should be equal, and they are equal. T cos theta will cancel t cos theta, and this t sin theta and t sin theta, 2t sin theta, 2t sin theta is the upward force. That should be equal to the downward force 150. Okay. So that means sin, that means 2t. You want to know the minimum tension. You need to find out the tension. So write an equation for tension. Tension is nothing but 150 divided by 2 sin theta. Or this is like 75 divided by sin theta. So when the body is in equilibrium, the tension will be equal to 75 by sin theta, whatever be the theta value is substituted. But what is asked in the question, you want the rope to be completely horizontal, completely straight. If the rope is completely straight, then this theta should decrease. The string cannot be like this one, it should be horizontal. Then that means this should decrease to 0. Theta should become 0. So for horizontal, exactly like to be horizontal, theta should be equal to 0. Okay. Then what is the tension? You calculate tension is equal to 75 divided by sin 0. What is sin 0? Sin 0 is 0. So this will become 75 divided by 0, which is not possible. Or rather, we can say this will become a very high value or infinitely large value, or not possible. So the option will be like this one, it will become infinitely large value, or it is impossible practically. You can't never keep it horizontal. Now we are going to deal with a very highly important concept. It's called conservation of linear momentum, the law of conservation of linear momentum. which is the reason for this action. What is that? You fire a gun, the bullet will go out and the gun will hit back. It's called recoil of the gun. Whenever you fire any gun, this will happen. Smaller gun, the hit back will be less. Larger guns will be very, very high. I will discuss this in the next class in more detail, but this is it. Now, when you jump from a boat to the shore, like you are on a boat and you are jumping out, then the boat will move backward. You can try this in a mall. If you can get to a mall, shopping trolley, trolley will go backward. All these actions are just because of conservation of momentum. Now, you can further go like a balloon. You take a balloon, you can take a balloon, inflate it and leave it, then this will fly like this. That's due to this idea. The rocket propulsion is due to this idea. All of them are based on one simple principle, and that is what we are going to discuss now. It's called conservation of momentum. The total momentum from an isolated system of interacting particles is conserved. Oh my God, what is it? You have a system of two particles where there are no external forces. That's what we call isolated. If there is no external force acting, then the total momentum remains constant. So you can write down the statement in a different way. Write like this: if the total external force is 0, then momentum of a system is conserved. Momentum of a system remains constant. Or you can write like this also: in the absence of external forces, the total momentum remains constant. I think that will be a pretty easy definition to write down. In the absence of external forces, total momentum remains constant. This will be easy. Same thing, the total momentum of an isolated. See, in the absence of external force means it's an isolated system of interacting particles. That should be remain constant. Okay, I'll explain this. Mathematically, I'm going to do this. Okay, mathematically, to understand this, you should know that See, you have studied that differentiation, d by dt is differentiation of a constant. Derivative of a constant is equal to 0. You studied this. So, if I have a value a and if I write dA by dt is equal to 0, what does it mean? If dA by dt is equal to 0 means a must be a constant. That means a will not change. A constant means a is conserved. A is conserved. So, if you know this one, my explanation will be very easy. Okay. Okay. Now, let us say, see, there is a body A, there is a body B, they interact. When they interact, say there is this body A and there is this body B, when they interact, they apply forces on each other. FAB, force on A by B, and FBA, force on B by A, and we know this is equal and opposite. And we also studied from Newton's second law. From second law, we know that F is nothing but dP by dt. Okay. So, now see FAB, where is this force acting? This force is acting on A. So, whenever force is acting on the body A, the momentum of A will change. So, we can say FAB can be written like a dPA divided by dt. Rate of change of momentum of A is due to the force from B, force acting on A. Similarly, FBA will act on the body B. As a result, its momentum will change. So, that can be written as minus dPB by dt. Since they are equal and opposite, I have a minus sign. I bring it to the left side. So, what will I get? I will get dPA divided by dt plus dPB divided by dt is equal to 0. You studied the differentiation, suppose you have a term u plus v to be differentiated, d of u plus v by dx, you studied that this is nothing but du by dx plus dv by dx, you know this. So, using that idea I can write this is actually differentiation of vector PA plus vector PB equal to 0. And I know that whenever derivative is 0, that means PA plus PB must be a constant. Okay. So, now let us go to the statement. Here these are called internal forces because I am considering A and B as a single system. Remember that one. If I consider A and B as a single system, then these are internal forces. These are internal. That means there is no external force. There is no external force, or this is an isolated system. So, in an isolated system, the total momentum is a constant always. Always initial momentum equal to final momentum. So, this you can learn as a derivation. How to start the derivation? You should write like this. Consider a system of particles A and B. Consider a system of interacting particles A and B. Then you can say the forces exerted by A on B and B on A are like this from third law. From second law, force is this thing. Then you write these steps, get the equation, and finally you get a statement like this. Then you can write, in the absence of external forces, the total momentum of interacting particle remains constant. Okay. That is the derivation of conservation of momentum. There are other derivations too, but this is the best derivation because this is about the instantaneous momentum, not average values. Okay. So, study this. The application of all these things can be done in the next class. Till then, bye.